the last speaker of the session is Raphael. And yes, and the title is Recovering the Homology of Immersed Manifolds. Please.
Thank you, Michael. I'm so glad to present this work. So it is about immersed manifolds and how to catch the homology. So let me recall you that an immersed manifold can self-intersect. For example, we have this lemniscate here that intersect in the middle. In general, an immersed manifold is given like that. So you have an abstract manifold that I call M0. You have an immersion here, U, and this map U takes M0 to the Euclidean space, and the image of the abstract manifold is called an immersed manifold that I call M here. So let me give you some examples. If the initial manifold is a circle, then an immersion is given by this lemniscate. So in this talk, when we will see a lemniscate, we'll keep in mind that there is a circle behind it somewhere. So the Klein-Bottle is an example of an immersion in the Euclidean space. This is a picture of a photo in Dallas. You see a bunch of roads that can be seen as a union of lines. And seen from the top, you see a bunch of intersecting lines. So this is an immersion of the abstract manifold. And so the last one is a famous data set in TDA. So these authors get a point cloud in a high dimensional space, and they show that it is actually the immersion of an abstract manifold, which is the union, the disjoint union of a Klein-Bottle and a sphere. All right, so the question is, I give you M, the image of the immersion, and I want you to give me the homology groups of M0, the original manifold. And a more practical question will be, if I only give you a sample or a closed set X, I still want the homology groups of the original manifold. So for instance, if you are given this nice lemniscate or this less nice sample, I want the homology groups of the circle. That is, for instance, in Z2, one connected component and one cycle in H1. Computing the homology of embedded manifolds or submanifolds is something well known in topological data analysis, but there has been less work on immersed manifolds. But I still want to cite these papers which goes in that direction. Okay, so to see these homology groups, we will use persistent homology. So usually when you're given a subset of the Euclidean space, in persistent homology, you build the check filtration, also known as a thickening filtration of your sets. And then you compute its persistent homology. That gives you a barcode which reveal the homology of your data sets. But here, if you use the check filtration on your lemniscate, you obtain a barcode that tells you the homology of the lemniscate. You see one connected component here in H0 and two cycles that corresponds to these two loops here. But we want the homology of a circle, right? So we will try to modify this set. We'll try to lift this lemniscate in a higher dimensional space in order to obtain a manifold, a submanifold, which has the homotopy type of a circle. And here I applied the usual check filtration on this lifted set. And you can read on this barcode that we have a circle at the beginning of the filtration, which is what we want. So to lift M, so here we have the immersion U, which takes M0 onto M in the Euclidean space. We will define a map U check, which goes from M0 to this lift space. Here I add a component R to the M, and we will endow each point of the immersion with another component. And the idea here is to choose F such that our map U check is an embedding. So we will obtain a submanifold here, which is homeomorphic to the initial manifold. And the map we will choose today is the tangent space map, which takes each point of the original manifold to its tangent space. This is a nice choice of F because under a mild assumption, we obtain the map U check, which is an embedding. And something which is also nice is that from this point of view, we are actually estimating the tangent bundle of our manifold. And tangent bundles, or more generally vector bundles, allows to define nice topological invariants such as characteristic classes. So this is something I've done lately. You can read about that on my webpage. So let me introduce some notations. Our immersion is called U. If I have a point now in my abstract manifold X0, I call X the image of X0 by the immersion. TXM will denote the tangent space of M at the point X. MRN is the space of n times n matrices. And when I have a tangent space, TXM, I will consider the matrix PTXM, the projection matrix on the tangent space. And our lift space will be this product, the Euclidean space times the matrix space. So it corresponds to this lift space here. So the lifting manifold is the image of M0 by the lifting map. So the lifting manifold is a subset of the lift space, which is defined as a set of pairs with a point in the Euclidean space and the corresponding projection matrix on the tangent space. So all is summarized here. You can think about M0 as a circle, which is immersed as a lemniscate. And U check takes this M0 into this submanifold of the lift space. So in this example, n is equal to 2. So the lift space is of dimension 6. And I just applied a PCA dimension reduction in order to visualize how it looks like. All right. In practice, you only have access to a point cloud X that we suppose close to the immersion M. And we want to build the set M check, the lifted manifold. To do so, we have to compute tangent spaces, and we will use local covariance matrices. So the local covariance matrix depends on the radius parameter R. And basically, if you pick a point X of your data set, you look at all the points Y that are at distance at most R from your points, and you compute the sum of tensor products. That gives you a matrix, and you can show that it is close to the tangent space. It is close to the projection on the tangent space. And I don't know if you can see the definition of X check, but it's X check, so it's the lifted set. It is a set of Euclidean points endowed with their local covariance matrices. It is a subset of the lift space. But what happens is that, so this is X check, and you see there are some outliers in the middle. This is because when we compute local covariance matrices, this works well when we are away from a self-intersection, but close to the intersection, the local covariance matrices are not good estimators of tangent spaces. And as a consequence, our lifted set and the theoretical lifted manifold are not close in orders of distance. So we cannot apply a usual persistent homology. Though they are close in some other metric, namely the Wasserstein metric, which is a metric between measures. So we have to adopt a measure point of view. That's what we'll do right now. In this new setting, M0, the abstract manifold, is endowed with a measure that I call mu0. The immersion U will take mu0 to mu, and U check will take mu0 to mu0 check. So from now on, the object of interest is mu0 check. If mu0 has full support, then mu0 check will have support M check. So we will be able to recover M check from mu0 check. And notice that I added a normalization factor here in U check just for technical reasons. So let me give you another definition of mu0 check. So ici, it is a measure on the Lift space. If I take a test function on the Lift space, then integrating along mu0 check is the same as integrating along mu0 on the abstract manifold with this change of coordinates. Now, in practice, we are observing not mu, but nu, a closed measure. And we will lift this measure in the Lift space via this definition. So I take a test function, and I say that integrating along nu check is the same as integrating along nu in the Euclidean space with this change of coordinates, where sigma nu is the local covariance matrix for a measure. And so yeah, we have a theorem which tells you that nu check is a good estimator of mu0 check in Wasserstein distance. So we need the parameter R to compute local covariance matrices. And we suppose that the initial Wasserstein distance between the measures is small in the Euclidean space. So there are serious assumptions that have to be made on the immersion and on the measure that I won't have the time to describe, but what you get at the end is a bound on the Wasserstein distance between the theoretical lifted measure and the actual lifted measure that we can compute. And this result holds for any P. All right. So now we have a measure and we want to compute homology. So we'll use persistent homology for measures. There are several ways to do that. I will describe something we presented last year, which is called the DTM filtration. So let me recall you that when you have a subset of the Euclidean space, the check filtration is the collection of thickenings of your set. That is a union of balls centered around points of your set. Now, if you have a measure, the DTM filtration is a collection of these spaces VT, which are also union of balls centered around the points of your support of the measure, but with radius t minus a weight function. And the weight function here is a DTM. So this is an outlier robust function. So basically you postpone the apparition of points in your filtration if the weight is too high. So it looks like that. This is our lifted set, X check. And you can see that in this filtration, you grow balls around points of X check. And these outliers appear late in the filtration. So we actually see a circle at some point. All right, so this is what we get at the end. The persistence diagram of the DTM filtration looks like that. And you can see that there is a window here where we have one connected component and one cycle in H1. So you can say that this is a circle. There is a circle behind this lemniscate. All right, I think I have a last illustration. It also works for noisy data sets. So this is the 5 Olympic rings that you have to see as the immersion of 5 disjoint circles. But seen in the plane, they intersect. And we want to get back to the 5 circles. So you lift this set in R2 times the matrices. You apply DTM filtration and you get this diagram. And you can see that here we have 5 connected components and 5 cycles. That is 5 circles as we wanted. And that's it. Thank you.
Thank you, Raphael. So there were 2 questions in Discord, one by Morten Prune. What is D in the normalization?
Yeah, D is a dimension of the manifold. Because I prefer to estimate mu0 check with the D inside so that we don't have to use the D in the definition of mu check, because we do not know the dimension of the manifold at the beginning. So, yeah.
Okay. The second question is by Oleg Kahan. So you have ellipsoids in the first case and balls of different radius depending on the density in the second?
I don't have ellipsoids, only balls.
Yeah, Oleg, if you want to unmute and clarify your question. Otherwise, I think it takes too long if you type.
The local covariance matrix is like a deformation of the ball according to the eigenvalues of the covariance matrix in the directions of the eigenvectors. No?
Yeah. Yeah. So
So in some sense, it's a filtration of when the balls are actually deformed to ellipsoids.
Yeah. Yeah. You could try to grow ellipsoids on your data sets, but there is still this self-intersection issue, right? So the idea here is to take the local covariance matrix as it is and add it, endo it to your data sets. So if you project what you get in the Euclideans, yeah, no, I mean it does not use ellipsoids, but it's quite related.
Okay. If there are no more questions, then yeah, this is the end of the session. I want to thank everybody for listening, for the questions and discussions also on Discord. Thank you.